Hmm, hmm.
Whenever you are ready, I can start letting people in.
Okay, why don't you start? Well, greetings, everybody. It's 1 o'clock, so we're going to start lecture three of our cosmology class. And today we're going to focus on expansion of the universe. In class number one, we talked about this surprising result that dates from the end of the 1990s. And there's a little history behind this, so I thought I'd talk about that for a second. Hubble Space Telescope was launched in 1990, and very quickly it was discovered that the performance that was expected was just not there. There were big problems, and it took an intense team effort to figure out what was wrong. The images were, to say it in a standard way of thinking about it, images were out of focus. It's a more technical thing than that, but that's a good way to describe it. And the result was the scientific productivity of the Hubble Space Telescope was compromised. And there was enormous pressure on NASA and the institution that runs the telescope, that's based in Baltimore, to explain to Congress why these very expensive telescope didn't work. Ultimately, the problem was found, and many of you know that it was determined that the primary mirror, it's a 10 feet in diameter, um, was defective on the scale of a fraction of a human hair. And this, of course, got repaired in 1993. Astronauts put corrective optics into Hubble. That design for that was done by the people at Ball Aerospace in Boulder, and that was a success. So the scientific productivity of the Hubble Space Telescope didn't really start until roughly the middle of 1993. And there was a huge backlog. You should know that when new telescopes are built, or even when old telescopes are scheduled, there's a series of proposals made by astronomers for viewing of certain objects for certain periods of time and so forth. And so, because it took 3 years to fix Hubble, there was a backlog. And not until the, okay, I see there's a question about the class folder. Uh, I'll work on that during the break. Anyway, Hubble got fixed, and it took a while before a research program initiated by two different groups finally got a chance to look at supernova events, that is, exploding stars. And they collected data, and then they had a couple of years of processing of the data. And to their surprise, both groups independently found that the slowing of the expansion of the universe that everyone assumed was how nature was working, that turned out to be not the case. And in fact, the opposite was true, the expansion rate of the universe was increasing. And that was a bombshell and led to a Nobel Prize. And today we're going to talk about the details of this type of discovery. Before we do, let's talk about last week's questions. Here we are. Hawking and Penrose discuss a singularity at the Big Bang. That is, that there was a beginning for the universe. And the question relates to, is there any evidence of the singularity? And the answer is no. The light we can see, the oldest light we can see, is the cosmic microwave background. And that dates to 380,000 years after the beginning of our observable universe. We don't have any vision prior to that because any light that was produced earlier than the cosmic microwave background had to propagate through a plasma of atomic particles and pieces of atoms, and there would just be no sensible information. It's like looking through a fog. There is hope, however, that our new capability to detect gravitational waves might contain information about the very early universe, and that is an active area of research. The gravitational wave observatories we have now cannot see that type of gravitational wave. There are, due to the size limits of the observatories we have now, the gravitational waves we would expect to see are not detectable. However, we can press in that direction with a new space-based gravitational wave system. So there's more news coming on that. It's going to take some years, but we may have a way to see earlier in the universe using that approach. The second question has to do with somebody with some math skills said if the velocity of something is greater than the speed of light, Einstein's equations preclude that from being allowed. And how is that possible? And so I've included this piece of art. We're going to see this again at the end of this presentation. As we look back in time, and remember we do that looking at the redshift value, the farther back we look, the faster things seem to be receding from us, not because they are moving through space faster than the speed of light, like this symbology would suggest, but rather because the space between us and that distant object, that space has been expanding for the entire life of the universe, and there's no limit on how fast space can expand. And in fact, what I've shown here is a calculation of, if we look back very early, this is about the time of the cosmic microwave background, which is at 1100, a redshift of 1100. You see that the speed of anything back at that point is more than 3 times the speed of light. And we've just had to come to understand that that's allowable. The objects at that distance are not moving through the local space faster than the speed of light, but the expansion, the cumulative expansion of the universe since the Big Bang until we are now looking at distant objects, that accumulative expansion rate is now more than 3 times the speed of light. So Einstein is resting easy on that. Let's see, another question. If baryonic matter, that's atomic matter, is 4.5% of the universe, and stars are generating more and more heavier elements, is there a net reduction in lighter elements over time? And the answer is yes. However, the lighter elements, principally hydrogen, will fall to a level and just never go any lower because hydrogen is used to create heavier elements in stars. And star formation is, in the far future, is going to stop. The universe is going to be so enormous that gas that would otherwise collect to form stars just won't be able to do that. The gravitational attraction will be too small, and new stars will not be forming. We're talking about way in the future, 100 trillion years or so. So there will be fewer places for heavy elements to be formed. What's more, hydrogen is, even today, almost all the hydrogen in the universe is in clouds of gas floating between and among the galaxies. And that gas has not yet formed stars and is unlikely to in the future. So, and that just clouds of gas will not have the pressure and temperature to form new heavy elements. So we expect gradually the production of heavy elements by forged from hydrogen will stop. So yes, there will be a gradually growing fraction of heavier elements, but that's going to stop as the universe ages. There's a question here about if no dark energy existed, what is it a property, or say it another way, is dark energy a property of space itself, or is it somehow being created? And we don't know, but most of the evidence we have suggests that dark energy is a property of space, and it's a topic of research to figure out why space behaves that way. Let's see. And then there's a statement here by the person who asked the question that's exactly right. You can read that at your leisure. Then there's a question about what is dark matter, and there's been suggestion that dark matter is in the form of atomic-sized black holes. And the question is could that be the case? And there's a big problem with this. Stephen Hawking, 35 or 40 years ago, predicted that all black holes evaporate, and the tiniest ones evaporate extremely quickly. In fact, here's the formula for the time it takes a black hole to evaporate away its energy. And if we put in here for the mass, m cubed, and here's some constants, just do this arithmetic, and we find a hydrogen atom, if it was in the form of a black hole, would evaporate in this extremely short period of time. So any black holes formed, for example, in the Big Bang, would have disappeared almost instantly and not be around to behave like dark matter. We know quite a bit about how the influence dark matter has on the formation of galaxies, and we do not see any evidence for very tiny black holes, like atom-sized black holes, actually being around long enough to influence formation of galaxies. And then there's a question, I brought this up last time, about there might be a fourth type of neutrino. There are little hints about this in the data we get from the cosmic microwave background and from research done at CERN in Switzerland. And the question is, what would happen if we found a fourth neutrino? And I have a discussion here pointing out that CERN is looking for this. It's called a sterile neutrino. And it would be a revelation that if there's a fourth kind of neutrino, that means there's a fourth member of the family of electrons. Remember, there's an electron, the muon, and the tau, each with electric charge and an associated neutrino. So if there was a fourth type of neutrino, that would imply the existence of a fourth type of electron, and that would definitely stir the pot, but we don't know yet. All right, so let me just remind you where we were last week. We talked about the methods that have been employed that are generally called concordance, different types of measurements such as supernova events, which critically depended on fixing the Hubble Space Telescope, the cosmic microwave background, and I showed you last time the succession of space missions that have refined our understanding of this cosmic microwave background, baryon acoustic oscillations, that is correlation between warm and cold regions in the cosmic microwave background and where galaxies formed. We put all that together and include the way light propagates in the universe, the so-called lensing. And we have a very precise understanding now of the partition of energy in the universe between matter at about 31% and dark energy at 69%. Now here's a depiction of how distant galaxy light from an ancient large galaxy, usually called a quasar. These are objects that contain a supermassive black hole that at some point in its life had plenty of energy to consume and produced energy at stupendous levels, so bright that we can still see this ancient galaxy, even though it's located tens of billions of light years away from us at this point. And that light gets distorted, propagating to us, and we can use those distorted light rays to tease out things. So that's where we were last week. We also talked about this artist rendition of the expansion of the universe from an unknown source. Right here, it's associated, they're putting this label on it. We'll talk about this more. A period of inflation, very rapid growth in the size of the universe, and then the emergence of a much slower expansion, including the acceleration, this part of the curvature here of what looks like the horn of a trumpet. That curvature is intended to suggest that what was found in the late 90s is a real physical effect, and the expansion rate of the universe is accelerating. And that's our topic for today. So this was also something we talked about last week, and I overlooked letting you know that when we talk about dark energy, you'll also see in various news articles and books and so forth, different names for this dark energy that we've been talking about. Quintessence is the idea that dark energy's properties have changed over the life of the universe. And that's always in the back of people's minds when they're doing work on the properties of dark energy. Is it the same now as it was in the early universe? And quintessence is the label they put on that variable type of dark energy. Einstein called it a cosmological constant. And for a time, there were laboratory efforts to detect the physical properties of dark energy by studying the energy in vacuum. And we understand the issue of energy in a vacuum. It has to do with quantum fluctuations, particles that pop into and out of existence. And that is allowed by quantum mechanics. And we've measured the properties of the vacuum energy predicted by quantum mechanics. And we have a theory that works. We can predict exactly how much that energy is. But we'll discuss this in a future lecture. This is not the dark energy we see out in the universe. The difference between these two forms of energy is enormous. And in fact, if the vacuum energy that we find in the laboratory was the vacuum energy in space, the universe would have expanded so quickly that there wouldn't have been time for stars or planets to form, and we would not be here to enjoy this universe. So let's now get into the expanding universe that has created such a revolution in our understanding of cosmology since the late 1990s. One approach to trying to describe this and giving us all a handle on the dynamics of the expanding universe is to think about raisin bread. So we have a lot of dough with raisins uniformly mixed into the dough. We put it in the oven and it expands. The raisins do not get bigger, which is why I did not increase the size of these dots, but the space between them gets bigger because the dough, which is like the space-time between the raisins, that can expand in a heated environment. Now, we want to be careful when we use these kinds of images to talk about expansion of the universe because this loaf of raisin bread has boundaries. And our universe does not behave that way, does not have a boundary. And anything that has a boundary implies that it is embedded in a larger volume. The universe doesn't work that way. We understand, like I explained in our first lecture, understand the geometry of the universe well enough to know that it is an unbounded flat geometry whose space is unknown, but it does not have a boundary. And we'll do this in the next slide in a little more detail. So be careful when you use this kind of an analogy, because it's very easy to fall into the trap of thinking that the universe has a surface, and it doesn't. So let's go on to, there's some words here similar to what I just said. Let's think more about this type of geometry, where we have in the early days, the universe is small with galaxies. And over time, the universe got bigger and the galaxies become farther apart. But the influence that causes the universe to expand, the dark energy, is very weak compared to the influence of gravity. And gravity is what forms and holds galaxies together. So we don't see galaxies being bigger as the universe expands, but we see them being farther apart. And then I've got a third panel here to show the continued growth of the universe. And I just a minute ago mentioned that the geometry of the universe is flat. We get that from the cosmic microwave background. And it's kind of mind-bending to figure out how a flat surface, a flat space, is actually related to a spherical space. And the answer is, if the universe is large enough, we would not be able to detect the curvature. If you go outside right now and measure the flatness of the street in front of your house, you're going to find that it's flat to within your ability to measure curvature. And that's only because the technique you might have has to overcome the fact that the radius of Earth is over 6,000 kilometers. So what we don't know now is if we have a flat geometry, that our universe has a flat geometry, is that because it is exactly flat and boundless, or is it because the radius of a sphere that we reside on, the radius is so large that we're not able to detect the curvature? So that's, once again, a feature of this question about having a flat geometry, but not knowing the shape of our universe. Another feature of expansion of this kind is more distant objects recede faster. If you happen to be on this galaxy, which started here, and you watch this galaxy, as this analogy, this spherical analogy for our universe expands, you will see the distance between these two, the one you're on and this one, that distance will, the that object will recede from you faster than a nearer neighbor that is also undergoing expansion as this geometric object gets bigger. I'll show you more on this in a second. Another feature of this type of expansion is that all observers see objects recede from them. No one can claim to be the center of the expansion in this type of universe. So if you aren't on this object, but you're over here, and you watch these three objects recede from you, you'll see them all recede from you. And this observers on this galaxy will see these three recede. So every observer in the universe sees objects moving away from them in an expanding universe. Now, I got to point out that the math that was done in the 1920s that showed that the universe could be dynamic does not exclude a collapsing universe. In that case, all objects in the universe would appear to be coming at you, but that's not what we observe. We see distant objects going away from us no matter where we look. That's the big discovery that Edwin Hubble made in the 1920s and 30s. So one way we talk about this mental challenge of how we are dealing with an expanding universe and the fact that it has no edge is to imagine that we're sort of like ants on this sphere, walking around but only aware of two dimensions. An ant on a sphere can go forward, backward, left, or right. And no matter how much they move, they never encounter a boundary. That's why I emphasized in a previous slide that we do not have, this universe does not have a boundary, because that would imply that it's embedded in a larger volume. And we're very confident that that is not the case. So ants on a sphere have no sense of up or down because they are on a two-dimensional surface. And one interpretation of our situation is that we are in exactly that type of circumstance. However, that we are not on a sphere like the one I pictured here, a two-dimensional sphere. And it's two-dimensional because it only takes two numbers to define a spot on this sphere, that perhaps we're on a higher dimensional sphere surface. So there's language here again talking about the fact that there's no boundary to this. An ant walking fast enough on an expanding sphere can come back to the point where they started. So that gives you something to ponder. And here are the ants on the sphere. And this page with the big red dot is one of a few I've included for you to read to try to digest what we're talking about. Because this is not normal in our experience to be related to a volume of space that has no edge. Now, we want to make some other points about this expansion. Unfortunately, it pops up in the literature all the time, particularly in just general media, that the Big Bang was like an explosion of a bomb where parts were thrown out from the center of the explosion. That's not our case, because a bomb blows up in a pre-existing void. We don't have that. The entire universe expanded at the same time, and all of the energy in the universe was affected by the expansion, whether it was light or particles. Every place in the universe underwent the expansion at the same time. And as I've pointed out, we are not at the center of the universe. We are one observer in the universe. Other observers far from us see a different collection of objects moving away from them. And I've re-emphasized here, there's no edge to the universe. and yet it has a flat geometry. So this is all confounding. So here's an example of a slinky. We all probably played with one of these as a kid. If you lay this out initially with the coil has equal spacing between the elements of this spring, such like I've shown here. And then if you pull on the two ends, here's one of the ends and the other end. If you pull on that, the rate at which the coil, these individual loops, the rate at which they separate depends on how far they are from the end. And so if you happen to have a slinky around, you can play with that and see how that works. We have a measure for this, the speed at which the universe is expanding. Here it is. It's called the Hubble constant. And it's has some strange units. It's inverse time is what it is. And one of the values we have from the variety of measurements we know how to do gives us this number, that the expansion rate of the universe is 72 kilometers per second. So kilometers per second is a velocity if the object is 1,000,000 parsecs, or about 3 million light years from you. So an object 3 million light years from us, which is sort of like 10 times the size of our galaxy, that object is receding from us at 72 kilometers per second. That's a normal kind of speed. It's like 4 times the speed of a satellite orbiting Earth, much smaller than the speed of light, but that's for an object that is roughly 1,000,000 light years away. If we then look at 1,000,000,000 light years away, that's 1,000 times bigger than this. So the velocity of an object 1,000,000,000 light years away is 1,000 times this velocity. So that's how the Hubble constant works. And I've already told you that we have issues measuring the Hubble constant. We're going to go into that in more detail today, that we have multiple ways to measure the Hubble constant and they don't agree. And that's propelling a lot of research. And by the way, if we take this expansion rate to its extreme and look at the most distant object, namely the cosmic microwave background, it's 45 billion light years away from us. And if you go through the math, and I'll show you a graph that describes this, that turns out to be 3 times the speed of light. So again, we are not offended by the expansion of space. We would be disturbed if we found that galaxies were moving through their local space at more than the speed of light. And here's another one of those pages designed to give you something to read to try to explain these issues. I just make this point. Here's planet Earth. And the farthest thing we can see is the microwave background. And it's kind of like a ship. Imagine a ship here in the Indian Ocean. There's a horizon around that ship beyond which it can, because of the curvature of Earth, cannot see beyond that horizon. And if you have a ship with a very tall mast, you can increase the horizon. But nonetheless, there's still a horizon that's the limit of how far you can see. And that's a way to think about our situation, that there's a horizon around us with a radius of 45 billion light years, and we can't see beyond that. So let's talk a little bit about the history of the discovery of expansion. In the early 20th century, the assumption was that the universe was a static place filled with stars that somehow were put there and were perennial. And the presumption, original presumption was that stars produced light by chemical reactions. That was in the 1890s. Eventually, enough understanding of chemistry and the energy level of, for example, our sun, that put those things together, you realize it can't be a chemical reaction. The sun would have only lasted a few million years. Not until the beginning of quantum mechanics and nuclear physics did the real source of energy get uncovered. And it is a nuclear physics process where hydrogen is fused into helium and other elements. And that we understand will keep our sun burning for 4 to 5 billion years. But it wasn't until the late 1930s that the details of that process were understood by the Nobel Prize winner Hans Bethe. And prior to Edwin Hubble's work in the 20s and 30s, the presumption of a static universe was not confronted by any observation. Hubble was the first to see distant objects moving away from him, and that gave the first indication that the universe is not static and that more distant objects are moving away faster. And right in the middle of this, Einstein provided a key discovery, and that was his theory of gravity. And that was quickly put to work to understand what the properties of gravity implied for the behavior of the universe as a whole. That was the work of Friedmann and Lemaitre in the 1920s. There's Einstein and Lemaitre, a priest, and Friedmann. And the calculations done by Friedmann and Lemaitre using Einstein's theory as a starting point showed that there could be a massive universe, massive enough that gravity would overtake any expansion induced by the Big Bang, and that universe would collapse. That's allowed by the equations. You could also have a similar case where you had a Big Bang here and an expanding but decelerating universe that is slowing and slowing, but not slowing enough to recollapse. And then there's a solution that's sort of on the knife edge between these. That's a universe that is always expanding and there's no indication of slowing. This is the universe that was imagined in as late as the mid-1990s, before detailed measurements were made using the Hubble Space Telescope, looking at exploding stars. And we'll talk about why that was important. And they didn't find this or this. They found this, an accelerating universe dominated by dark energy. Here's another way to look at the same thing. If you have the universe we live in, there's an M there for matter, at 30%, and then there's this dark energy component at 70%, then you have a universe that has grown to its current size, right here, and that will continue to grow at an accelerating rate. If you have a universe that's dominated by matter and doesn't have dark energy, it would grow to the size it has now and then collapse. That's this possible future. And you have these others in the middle. And we now know this is the one this is the universe we live in. Now, let's look at Friedmann's equation, and we're not doing math here. We're treating his equation as a piece of art that we can use to give us some suggestions for what's going on. Friedmann's equation looks like this. This is the Hubble constant that he predicts based on the Hubble constant now, that is Hubble constant being the expansion rate that we now observe. And it's made up of 4 components. Radiation, that's light, matter, energy associated with curvature of the universe, and dark energy. And each of these contributes in its own way as the universe grows. And this parameter A is the indicator for the size of the universe. So if you take your grandson, who's now a foot and a half tall, and say that's equal to A equals 1. He's 18 months old. You put a mark on the door jamb, as we did in our house. And from then on, you measure the height of that child in units of 18 inches. So he's 18 months old, he's 18 inches high, and that's, we would say A is 1. How does A evolve as he grows? A gets bigger. And the question for not a child, but for the universe is, why does it grow this way? Well, Friedman developed this, and let me tell you what these terms mean. The light in the universe gets diluted as the universe gets bigger. So at the beginning, there were enormous number of photons of light. These are little clumps of energy that describe the wavelength of the light. So we start out, if we have a universe filled with light, we have a stupendously large number of photons. But as the universe grows, two things happen. The photons get farther apart because the space between them is increasing. It's a dilution, as you might expect. If you take a volume of gas and make the volume bigger, the atoms in that volume are farther apart. So that dilutes the energy density of light. But an additional thing happens. Light has a wavelength. That's its characteristic property. If you know the wavelength, you know the energy of that light. In an expanding universe, the wavelength gets stretched. So the photons undergo two effects. They get farther apart, and their wavelength gets stretched. So the energy density of the original light in the universe gets diluted by the fourth power of the size of the universe. Three of these as a result of the volume getting bigger, and an additional one for stretching of the wavelength of the light. Atoms and subatomic particles get diluted in the expansion, but they don't have a wave-like property, so they are affected at the cubic or volumetric expansion. The curvature, turns out, depends on the square of the size of the universe, and dark energy does not get diluted. If you have more volume, you have more dark energy. It just spontaneously appears for reasons we don't yet understand. So using this equation, you can make predictions such as Friedman and Lemaitre did. And Lemaitre was the one who realized that the current universe, if it was expanding, had to have been smaller in the past. And if you went back far enough, you would discover what he called the primeval atom from which the entire universe emerged. We now call that the Big Bang. And then we have a happy coincidence that this is work being done in 1922, 1927. Unbeknownst to these people, Hubble, almost at the same time, was observing an expanding universe. So everything was in place to discard the idea of a static universe. And what's more, Friedman put it in terms that where we can do calculations and see, depending on details, we can find how our universe is going to evolve. Now, it turns out we can simplify this equation. There's still light in the universe, but it has almost no effect. It was important for the first few 100,000 years, but as the universe expanded and the wavelength of the light got stretched, this factor in doing this calculation became unimportant. In addition, we now know the universe has a flat curvature. It's a flat geometry. So this term right here is 0. So this term doesn't matter. So we end up with taking Friedman's pretty complicated equation, and it becomes this simpler version of a technique we can use to calculate the future of the universe. And here's the calculation. If we have a universe that only has mass, it would grow according to this blue curve and get larger as a function of time with a exponent of 2/3. If the universe is only filled with light, of course, we wouldn't be here, but the universe would be following an expansion dictated by this orange curve. The universe would get bigger as the square root of the time or the age of the universe. Instead, what we find is this green curve, an exponential growth. And we'll be talking about that for the rest of today. So here's Hubble in one of the telescopes he used. Let's point out something I mentioned in the first lecture. Hubble exploited the redshift in the light of galaxies he saw to determine their velocity relative to him and his telescope. He had to also estimate the distance to the objects that he saw, and this was, when he was doing most of his work, this was a very difficult problem and filled with all sorts of errors. We are doing a much better job now, but the important thing is he used redshift to determine the velocity of distant objects and concluded that the faster something is receding from us, the farther away it is. He did not realize that he was looking at galaxies traveling through space, a static space, that were moving away from us because they were moving through a common space that we all were embedded in. In fact, the galaxies he observed are moving away from us because the space between us is not static, it's expanding. And we now attribute that to dark energy. And here's a little footnote about redshift. We've talked about that before, but can never have too much information in this field of endeavor. So here's yet another one of his telescopes and a note from an astronomer who has a very nice book. I recommend it. It dates to 2018, I think, in which she points out that Hubble did not encounter the idea of an expanding universe. He thought that objects were moving away from him through a common space, not a static space. And we have an analogy we can use here, and that's a boat. If you're standing on the shore of a body of water and a boat goes by, there's two possible reasons for that happening. One is the water is moving relative to you, carrying the boat along. That is, you're standing next to a river. The other is the possibility that the boat has propulsion through the water, like you would see if a boat was moving through a lake. Or both things can be happening. And it turns out virtually all of the velocity that Hubble saw in the objects moving away from him was the result of space expanding. The objects actually do have or can have motion in the space in which they're embedded. That's called proper motion, but it's ignorable on large scales. So let's take a look at this redshift issue. If we have a spectrum of some atomic species, as we do here in a laboratory, and we look for that same set of lines, the fingerprint of that, perhaps it's oxygen or hydrogen, and we look at a nearby galaxy, we see it, and can you see that these arrows indicate there's a little tilt, slight tilt, indicating that the light we get from that galaxy indicates a velocity relative to us, but not much because it's a nearby galaxy. A distant galaxy has the same fingerprint, but it's much different. It's shifted toward the red part of the spectrum because that distant galaxy is moving away from us. And a very distant galaxy has even bigger shift. So if you take this line, it's this line, it's this line, and this line as you look at more distant objects. In fact, we can get the rotation rate of galaxies by, here's a galaxy might be rotating like this, counterclockwise in this drawing. The gas and dust over here in this perimeter spot is actually moving toward us because it's circling around the galaxy. So we actually see a blue shift for objects coming toward us, and we see a red shift for material moving away. So by using the same technique, we can get the rotation velocity of galaxies because different spots in the galaxy have different red shifts. So here's a picture of one of Hubble's results where he estimated the distance and measured the velocity. And unfortunately, his technique for measuring distance was rather restricted. And so this line is what he drew back in the 1930s. The actual result we get today is quite different, but we have much better technology now. You should also know that if we measure the Hubble constant, remember it's a number, typically around 70. If you flip it over, that's the age of the universe. So if you're uncertain about or make a mistake about your measurement of the expansion rate, you're going to make a mistake about the age of the universe. We'll get back to that. So how do we get the distance? Hubble had limited capacity to do this. There's what we call the distance ladder, and we can use different techniques for different objects depending on their distance from us. If you want to know where Venus is, we can send a radar beacon out there and measure it. If you're interested in stars near us in the Milky Way, you can use parallax. That is, you can make measurements of the positions of those stars against more distant stars in the background, and then wait 6 months and make the same measurement, and the distant stars will not have appeared to move, but the closer ones will, and a little geometry will reveal the distance to those nearby stars. You can look at the aging of stars. This is not a technique that's particularly popular now, but a key technique is to look at variable stars, because if you can pick out a star with a particular chemistry that has a pulsation to it, gets brighter and dimmer, if you can classify Cepheid variable stars and find them at different locations, and assume their energy output is the same, then you have what we call a standard candle. A distant object looks dimmer than a nearby object. A distant object looks dimmer. And if you have a class of stars that behave the same way, have the same chemistry and dynamics, then you can measure the distance by looking at the brightness. And this was a scheme invented by Henrietta Leavitt using what we would now consider very primitive techniques, but nonetheless, she had a lot of success doing this. And what's more, if you can find a Cepheid variable star and an explosion of a white dwarf, a supernova, near that, the Cepheid tells you how far away the explosion was. And if you see similar explosions elsewhere in the universe, you know the energy output of that explosion, and that's a different, better standard candle. So let's get into what goes on in this ladder. So here we are at Earth making measurements of nearby objects. We're going to start this as an animation. And we're looking at a nearby Cepheid variable. But we know the distance because we can use that parallax technique, a geometric technique, and get the energy of the Cepheid variable star. If we find a similar Cepheid variable star farther away, we know the distance because we know the energy output of this time variable star. If we then find Cepheid variables near supernova explosions, the Cepheid reveals its distance because of its energy output related to its brightening and dimming, and the local supernova event, then its distance is known. And then we can use that to look at distant galaxies if we can find supernovae of the same type in the distant galaxy. So we have to build this. Hubble did not have this. He was confined to nearby stars and galaxies. Now we can reach out billions of light years into the universe to do this kind of work. So there's a description of this. The ladder, the so-called distance ladder, works because the satellite galaxies, the small galaxies called the Large and Small Magellanic Clouds, are visible from the Milky Way where we live. We can do Cepheid variables, and we've found, and that's what if you're in the Southern Hemisphere, you can see the Large Magellanic Cloud. Here's Henrietta Leavitt, and here's her result, that the period in days of these variable stars in the Large Magellanic Cloud, which is close to us, it's right there, there are Cepheids there, and there are Cepheids in the Milky Way that are behaving the same way. So if you plot the ones we can use parallax to explore, that tells us the distance to the Large Magellanic Cloud. And then we can extend this process. Here's the parallax technique, is just geometry. And that's due to Earth's motion around the sun. Here is the variation in the Cepheid variables, brightening and dimming. And here's Cepheid variables in a nearby galaxy, these circles. And right there, that blue cross is a type 1a supernova that occurred in the vicinity of a Cepheid variable. The Cepheid tells us where the supernova was, and that tells us how much energy was in the supernova explosion. And then we can go look for those similar explosions out in the distant universe. And here's one right here and how it evolved. Oh, this is the galaxy. And then we have the galaxy plus the supernova. And then we can subtract through a computer technique. You subtract the stars from the galaxy and you can see where the supernova occurred near a Cepheid variable. And James Webb is doing the same kind of work. Hubble did most of this, but the Hubble telescope did much of this. But James Webb is repeating this, reaching farther out into the universe. Here's an example in time of a supernova that occurred 1987 is the year it occurred in a nearby galaxy. And you can see how energy from the explosion is lighting up this gas and dust around the location of the explosion. And the supernovas are rare. We have not had one in the Milky Way since 1604, but we look at the Magellanic Cloud, and 1987A occurred there. So these are rare, but if we can find them, they're very important in building a cosmic ladder. So this is the remnant of 1987A, and here's a depiction of the dynamics of this type of supernova. It involves a binary star system where one of the stars becomes much larger and dumps a large amount of energy on a smaller white dwarf star, and the white dwarf can only exist up to a certain mass, and then it explodes. So that's the mechanism. And the telltale fingerprint of the supernovas that we are using is this time, it's called a light curve, how the brightness changes with time, and it is all caused by radioactive components in the exploding star. Nickel radioactively decaying along this straight line becomes cobalt of this isotope, and that decays to this isotope of cobalt. So if we see a light curve that looks like this, that's indicative of the type of supernova that we've calibrated using Cepheid variable stars. And this takes about 150 days or so. So you have to be looking in the right place to see the explosion. And then you have to pick out the events that follow this kind of curve. And it's all about how nickel isotope 56 decays to cobalt 57. Here's a collection of these supernovae. And if you're careful about picking the events you see, you can get information about the distance. And that's what the people did, what Adam Rees did, using Hubble Space Telescope data. And here's the key statement. Conclusive evidence for cosmic deceleration is actually an epoch of cosmic acceleration. And he and his colleagues won the Nobel Prize for doing this very tedious, difficult work. And an interesting feature of this is if you're a local observer right at the event, the explosion, you would see the rise and fall on a scale of about 40 days. But because of relativistic effects, we see that this brightening and dimming taking 125 days. It's because of expansion of the universe that the aging of this event gets stretched and changed. And it's the impact of expansion of the universe between us and this exploding object that causes the stretching of this brightening and dimming. We're going to skip this. We're at a break point. Let me do one thing. We talked about this a couple of weeks ago. Yeah, let's skip this and start when we resume in about 5 minutes. We'll start talking about the problem of measuring the Hubble constant. So let's take a break for 5 minutes. It's now 2 o'clock. I'll see you at 2:05. Okay, everybody, I'm back. I hope you had a quick break of your own. And I want to talk about one question that popped up, and it has to do with how do we know that the Cepheid variable that we pick out is next to or near the supernova event that we want to calibrate? And the answer is they both have the same redshift. So remember, redshift tells us velocity. So imagine a sphere around us that is expanding away from us. Everything on that surface of that sphere we're looking at the inside of that sphere, everything in that sphere, on the surface of that expanding sphere, is at the same distance from us because it has the same redshift. So, and if you look at enough stars in the Large Magellanic Cloud, for example, you find all the stars there have the same redshift, or we have measured the distance using another technique for something like the Magellanic Clouds. They're close enough to us that we can use parallax to make that measurement. And so there's different techniques for getting the distance, but once you have the distance and you have determined that two objects are near each other, then you can start comparing their energy levels, and that adds to the cosmic ladder. So now let's talk about the problem with the Hubble constant. Here's Hubble's work, where he estimated the distance and the velocity. I mentioned to you, I think in the first lecture, if you want to hear about the expansion of the universe and so forth, you might want to look at this little movie clip from Woody Allen's movie, in which a doctor explains to him that Brooklyn is not expanding, and that is true. Brooklyn and the rest of the universe, the galaxy, are not expanding. So here's Hubble's estimate for the expansion rate, distance and velocity. And here's early data from the Hubble Space Telescope from Bob Kirshner, 2004, where he was measuring the distance. Notice the error bar on the distance of distant objects is quite large. It's still, I mean, this is a big challenge, measuring the distance to things. And the error bar for the velocity is quite small. That comes directly from the redshift. So we have one set of data that's very precise, the redshift gives us, and we have another that's a little fuzzier. And this is, I've added this to Kirshner's drawing. This is Hubble's prediction. And over the years, the estimate of the Hubble constant, which started with Hubble back in the 1920s, we now know that the number is down here around 70. But this had some interesting implications for how much we could rely on this measurement, because geologists knew roughly the age of Earth back in the 1920s. And I remember I said that the Hubble constant, if you manipulate it with a little math, it tells you the age of the universe. So a large Hubble constant tells us that the universe is not very old. And that was a problem. In fact, here's the Hubble constant as a function of year. And here is what that implies for the age of the universe. if you take this data and plot it, use these numbers that come from astronomy and plot the age of the universe, you find that in the 1930s, the estimate was the age of the universe was less than 2 billion years. And that was a problem because geologists were beginning to understand the age of the universe, and they said Earth is between 1.6 and 3 billion years. This is 1927. So geology was saying the universe is about 2 billion years old. Sorry, the Earth is 2 billion years old. And astronomy said the universe is 2 billion years old. So how would the Earth have formed instantly at the beginning of the universe? Now you see how our estimate of the age of the universe has changed as we've gotten better and better results for the Hubble constant. And we now have an estimate that's sitting here at around 14 billion years. But here's where the geologists were in the early 1920s. Geology has settled into, and has for the last 60 years, settled into a value for the age of the Earth is 4.5 billion years, and the age of the universe is almost 14 billion years. So this early conflict about Earth being younger than the universe or the same age, that's finally been resolved. It took a century to do it. But we're still not happy about the Hubble constant. And I'm going to repeat for you in more detail what I talked about in the very first lecture. And that is, 20 years ago, everybody was happy that we were measuring the Hubble constant. Remember, I said a typical value is around 72. The error bars and the understanding of the systematic errors in measuring this by different techniques were not that well understood 20 years ago. And over time, we began to see that different techniques were actually refined, that we were getting refined measurements. But right around 2015, a gap appeared. So we have here in blue the supernova data that contributes to a measurement of the Hubble constant. And it's predicting a number sort of like 72, 73. The microwave background data is predicting a number much smaller, around 67. And 5 years ago, roughly, Wendy Friedman at the University of Chicago came up with another scheme I'll describe to you, and there was hope that it would resolve which of these is correct, and it landed right in the middle, which was not what we were hoping for. So we have several methods, and here's the difference between them. The supernova data reaches out into the universe 3 or 4 billion light years. That's as far out as we can find supernova events calibrated by Cepheid variables, and the invention, the building of the James Webb Space Telescope has improved the number of supernova events, but we're still somewhat limited. So the supernova events that are depicted here in blue, they're giving us data that's relatively close, derived from events that are relatively close to our telescopes here on Earth and nearby space. The cosmic microwave background information depicted in this pink color, that's a technique that relies on light propagating from the earliest time in the universe, from 380,000 years after the Big Bang. So we have two different schemes, and they don't measure the same thing. One of them is derived from data that reaches back to the very beginning of the universe. That's the cosmic microwave background data. And we have one that's relying on relatively nearby supernova events. And then this green area, this data that's here, comes from yet another thing. It comes from the techniques related to the aging of stars. Here's another depiction of the same thing. Here's the Cepheid variable technique, which includes calibrating supernova events, and here's the number there. Cosmic microwave background is here. This technique is the most recent attempt to resolve the issue, comes out in the middle, and this orange dot also kind of falls between the two extremes. This is related to lensing data because of some features that I'll show you here in a second. So we have a spread of numbers that gives us estimates of the Hubble constant somewhere between 67 and 73 or 74. That's about a 10% difference. That means our understanding of the age of the universe is uncertain on a scale of 10%. So there's some little labels I've put on here to explain. This newer technique from Wendy Friedman relies on the aging properties of stars and the feature of a star like our own that as it ages, it becomes a red giant. And there's a characteristic property, the tip of the red giant branch, I'll show it to you in a second, that can be used to get the age and distance from a particular star. To understand that, we use what's called the Hertzsprung-Russell diagram. So let's take a look at the axes of this. Different stars are placed in different locations on here. Here's the temperature of the star with the coolest on the right and the hottest on the left. And there's our sun sitting there at around 6,000 Kelvin surface temperature. And on this scale, we're looking at the luminosity, how bright the star is. And in units of our sun is at 1 luminosity and 6,000 Kelvin. As our sun ages, it will likely take a trajectory through this branch and become a red giant. There are other stars that have started with more mass or different chemical properties. They are in the supergiant class. And then we have this isolated group here, the white dwarfs, some of which become the exploding stars we use to calibrate distances to various galaxies. And the reason this is the Hertzsprung-Russell diagram. And so I didn't draw this, but I've picked out a particular trajectory here for a main sequence star, such as our sun. Again, here's the temperature, coolest on the right, warmest on the left, and luminosity. And a typical star might make this trajectory, depending on its particular features, and become a red giant. The interesting thing is, eventually that red giant gets to a certain luminosity, a very high brightness, and goes through a period in its life where its brightness does not change as it ages. And we can calibrate that brightness for a star that makes this trajectory, and our sun is a candidate to do this. So because the star ages and changes and its output brightness doesn't change, it can act as a standard candle. And we can find these out in the universe, calibrating them by different methods. Once we have one, we can count on it having the same temperature as it ages and becomes a white dwarf. And that takes a big part of 1 billion years for that to happen. So this method gives us a standard candle. And there's some language there to talk about. So that's another technique for trying to get the Hubble constant, because if you have calibrated stars whose output you can get the distance So let me repeat, the real problem in getting this accurate estimates of the Hubble constant is knowing the distance to stars and the velocity of the stars. The cosmic microwave background technique does not rely on this. It gives us the result immediately. So now let's talk about the delayed lensing effect. So let's just for a second, we're going to go back. I mentioned Cepheid variables calibrated are used to calibrate supernova events. We have the tip of the red giant branch. We have the cosmic microwave background that does not depend on the properties of stars. We just look at the properties of the cosmic microwave background as we did last week, and we can get the age of the Hubble constant from that. Here's delayed lensing. So let's talk about that. Delayed lensing occurs when you have a distant bright object that was active early in the age of the universe, and you have mirages associated with that because the light from that object passes near a massive object that distorts the path of the light coming to us. The light that gets to us by different paths can be identified as being associated with that one distant object because all these mirages have the same redshift, which tells us they're all coming to us from an object moving away from us at a specific speed. And by looking at the spectra of these, we can tease out the chemical composition, and they all have the same chemical composition. But we have another tool in our toolbox, and that's delayed lensing. Let me show you that. There's some words here I'll talk about. So here's the depiction of what's happening at ancient galaxies spreading light into the universe. An intervening galaxy causes the paths to us to be altered, and some paths are longer than others. And if you look at this, you'll see the time shift. This is that's 200 days right there. So there's a substantial time shift. And how do we know that these all are from the same object? Again, the redshift, the chemical composition, and the dynamics. This distant object, which is this distant object was fueled by a black hole, a gigantic black hole, a super massive black hole, eating whatever came into its neighborhood, and its diet changed on a daily basis. Sometimes there was a lot to eat, sometimes there wasn't. So the light output from this, the energy at the center of this galaxy, changes with time. And if you look at the orange curve here, it's bouncing around because right here, some big cloud of gas or dust or group of stars fell in, and the delayed signal that came some days later shows the same change in energy output. That tells us that we're looking, the orange curve would be a more direct route to our telescope, and the blue curve took a longer path. And that means that these paths are sampling different regions of space as they propagate to us. And because they're sampling different regions of space, because one path is shorter than the other, that can be used to indicate the expansion rate of the universe during the time the light propagated from that distant galaxy to our telescope. And so there's no question that these 4 dots are from the same source, or these 4 are from the same source. We now have enough telescopes looking at enough galaxies that we see many examples of delayed lensing. Here's an example. Here's light taken from the Hubble Space Telescope 10 years ago. Here's the same spot on the sky taken from the Webb telescope, and you see some similarities, but there are differences See, this spot there is this spot here. This arc is this arc, but this little dot did not appear in light coming to the Hubble Space Telescope. Sorry, it was noticed by Hubble in 2016 and was not noticed by Webb in 2023. And by careful analysis of these curves and the properties of the distant galaxy that produced this light, we can tell how much delay will be occurring. So we have, again, buried in this arc from, I don't know which telescope. You can see a little bright spot that didn't appear there. And from that information, we can tease out the Hubble constant, but we have different techniques, as I pointed out. Here's Hubble working in the 1920s and very limited understanding of the distance to stars. The supernova data lies along this blue line. The cosmic microwave data, which samples the entire universe, reaching all the way back to when the universe became transparent, that's on this line. And this is the gap we see. And this is, by the way, this is as far out as the supernova data go. So this, let's translate what this is. This is millions of parsecs. A parsec is about 3 light years. So this is 600 times 3 million. So this is about 2 billion light years out into the universe, and we run out of supernova data. So here's why it's important to know the Hubble constant. If we use the Friedmann equation, as I depicted earlier, and put parameters into it, we can see the expansion of the universe. If we say that today, 13.8 billion years after the Big Bang, let's call that A equals 1. Remember, A is like measuring your grandson in units of his height when he was 1 year old, which would be about 18 inches or 2 feet, whatever. We don't know the size of the universe, but we can say that we're just going to call its value today 1 here at around 13.8 billion years with the values that we are getting from the Hubble constant, the amount of matter in the universe, and so forth. This is the prediction for how the universe is going to evolve, that it grew rapidly in the early days and its rate of expansion was slowing. It got to this point, this is us today, but about right here, things changed. Dark energy began to propel an accelerating expansion, and we expect that to continue. Here's the equation that's used to do this calculation. If you have a math background, you'll recognize this. So how does this work? How does the information we get from astronomy dictate this curve? Astronomy tells us the fraction of the universe that is in the form of matter, both dark matter and atomic matter. And it tells us the amount of the universe that is dark energy. So we do some arithmetic there. And this is the square root of the dark energy. This is the age of the universe. And I remind you that we agreed the age of the universe comes directly from the Hubble constant. So if you have this wrong, your curve is not going to be correct. Here are the numbers I used to do this curve. Let's see what this means for the rate of expansion of the universe. In the early universe, the expansion was very high and it was slowing under the gravitational influence of the matter existing in a relatively small universe. The blue curve tells us how the expansion rate is going to change over the life of the universe. Here we are right here. That's 13.8 billion years after the Big Bang. And we see the expansion rate changed properties right here. It had a minimum at around 7.5 billion years after the Big Bang, and it's been under the influence of dark energy. But is it following this curve based on this estimate, the Hubble constant, or is it following this brown curve? It's quite a bit of difference because we have about a 10% difference in the Hubble constant. That's why everybody is bearing down on this problem, because a smaller Hubble constant means a more time since the Big Bang. So this remains a compelling problem in astrophysics and cosmology. And here are the words that describe the curves. Now, I've used the term Hubble constant. Let me show you how we get that. The Hubble constant uses both the distance to objects and the velocity of those objects. And it is the ratio of the velocity, which I've depicted here, and the distance. Now, we don't know the actual distance in light years or miles. We don't know the size of the universe, but relative to today, this is the expansion rate, which had a minimum at around 7.5 billion years. And this is the history of the expansion, the size of the universe. And if we put those together, we get this curve. This is how the Hubble constant is going to evolve over time. Again, we are 12, 14, we are right there with a Hubble constant around 70. Because of expansion of the universe, the Hubble constant is going to get smaller over its life. And eventually, far in the future, 50 billion years after the Big Bang, the Hubble constant, the expansion rate of the universe, is going to settle into a single value and always have the same value, because in this part of the history of the universe, the only thing that will matter is dark energy. The influence of gravity and light and curvature will all become so small they will have no influence. So the future, this curve tells us the history up until now, which is right here, and the future evolution of the Hubble constant. But we would like to know the Hubble constant without all this fuzz on it. We can also look at that curve by looking backward in time. Remember, redshift, indicated by Z, tells us the history. So here we are today at today's Hubble constant, and we look backward in time, and the farther back we go, the higher the rate was. That's another way to look at this. Now, we had a question last week about how do we know the universe is, or the most distant objects in the universe are 45 billion light years away? Why isn't the distance to the most distant objects just the age of the universe times the speed of light? And the answer is the universe has been expanding at its highest rate since it was born almost 14 billion years ago, and the impact on the velocity of different distant objects has been continuous. More time goes by, and those distant objects accumulate more velocity. So the ones that emerged from the Big Bang at near the speed of light are now going faster than the speed of light, and the universe is much bigger than you might have expected. Again, here's redshift, and here's distance. It's called the look-back distance. So if we have a nearby object, let's say with a redshift of 2, those objects are more than 17 billion light years from us now, if they still exist. We don't know if they exist because we're detecting light emitted in the early universe. Those objects could have been a very active galaxy like a quasar who ran out of things to eat, and the stars all ran through their fuel, and it's just a dark, dusty place with no light. But the light we have from it at a redshift of 2 tells us it's now 17 billion light years away. A redshift of 8 gets us to almost 30 billion light years. Now, what happens if we go to an even higher redshift? And we can detect galaxies at much higher redshifts than 8. So I'm going to get this text. So now this inset reproduces this graph, but it has a scale for Z, a redshift that goes from 0, not to 8, but to beyond 1,000. The redshift of the cosmic microwave background is 1,100. So if we follow this curve for a redshift of 1,100, we see that that surface of light that was detected by the various spacecraft that measure cosmic microwave background, that surface is 45 billion light years from us. And it all comes from building a look-back curve. So for a redshift of 1,100, we get the most distant surface we can see is about 45 billion light years away. Here's the equation that deals with this. Again, for this, you have to know the amount of matter in the universe. That's omega m. You have to know the density of dark energy, omega lambda. But you also have to know the Hubble constant. So this fact that we are measuring the Hubble constant using different techniques and getting different answers is a source of frustration because it impacts all of what we know about the past and the future of our universe. There's also related to, well, let me think, do I want to show this? Oh yeah, I want to make this point. Scientific American is the oldest science magazine published in the United States. It's been around since 1870s, I think. And they have to be more careful about what they do here. Because they wrote an article, this is a pretty recent article, 2022, in which they read a scientific article and that said that the most aged galaxy we've ever seen is 13.5 billion years old. This was new data coming from the James Webb Space Telescope 3 years ago. And the author, Stephanie here, just wrote a headline saying the most distant galaxy is 13.5 billion light years away. No, 13.5 billion years of age needs to be analyzed using the look-back curve. So we go to 13.5, it's right there, and we go up and over, and we find that object is not 13.5 billion light years away, it's 33 billion light years away. There's the actual number. And I occasionally, when I have a little excess energy, I will write to reporters and editors and point these problems out, that this is misleading. Well, it's not misleading, it's just plain wrong. This gal was very nice about it. She wrote back to me and said, I'm going to be more careful. I'll check with an astronomer before I write headlines like this anymore. But this is interesting. This tells us that James Webb found a galaxy that formed within the first 300 million years. So if you take 13.8 and compare it with this 13.5, that's 300 million years after the Big Bang. This is a topic we'll discuss in lecture 6, the revelations that have come from the James Webb Space Telescope about how quickly galaxies can form. So there's really two messages on this page. One is be careful about what you read. These mistakes pop up all the time. And second, the age of this galaxy, which I do not doubt, is really a surprise because it says that galaxies formed much earlier in the dark age that we've talked about before. And that was unexpected early emergence of galaxies. And that's still a topic of a lot of excitement due to measurements from the James Webb Space Telescope. Here's another example. I don't want to make too much of this, but somebody found a radio source that has a redshift of almost exactly 1. And from that, they concluded that this object is 8 billion light years away. That's not true. If you look on the look back curve, you find it's 11 billion light years away. So be cautious. Quite a bit of what appears in the press is incorrect because the writers are not scientists and they misunderstand what they're looking at. There's also a calculation you can do based on redshift from ancient galaxies for something called look back time. That is, if we look back, if we use what we observe to get the age of distant objects, we have to do a different calculation. We're looking at look back distance. Now we're looking at look back time. And if you look at high redshift objects, let's say a redshift of 10, that gets us in the range of 13 billion years of aging in the universe. So this object, observed by James Webb, has a redshift of a little bit more than 3, and that gives it an age of 11.3 billion years. The cosmic microwave background is a redshift of 1100. It's like off the chart, and it gives us an age of 13.8 billion years. That's where we get the age of the universe, is the redshift of the light that we see from different objects like galaxies, or the cosmic microwave background, which is the oldest light that we can detect. And we know the redshift because if you look at the content of the universe, you can identify, in the case of galaxies, you can identify chemical components in this galaxy and compare them to what we see here in the laboratory. For example, you look at oxygen or hydrogen or iron, whatever it is that's in that galaxy, and compare it to what we measure in the laboratory, and you immediately get the redshift, in this case, 3.1. Now, I already showed you this curve, but let's look at it again, and that is the cosmological redshift that's induced by expansion of the universe is not limited by Einstein's theory of relativity. Space can expand at whatever rate it wants to under the influence of the amount of matter and dark energy that exist within that space. Special relativity says we can't have an object moving through space faster than the speed of light. And as I showed you in the questions at the beginning of this talk, somebody had pointed that out. Yes, there is a speed limit for how fast objects can move through the environment in which they are located, but the cosmological redshift comes from a different source. It comes from expansion of the space between objects. And you see here why I said that for high redshift items like the cosmic microwave background, the speed limit is around 3.3. Here, I haven't quite gone all the way out, but there's the velocity is 3 times the speed of light right there. And actually, if you extend this out to the microwave background, you find the speed limit is at 3.3 times the speed of light. So now let's take a look, kind of beginning a wrap up here. Let's look back in time at what's been observed by the Hubble Space Telescope. So it looks at modern galaxies, measures the redshift. And using the cosmic ladder that I talked about, by using supernova events, we get the distance to these. So Hubble is able to reach back from a redshift of 0, which is objects right next to us, can reach back into this period back here, earlier times when there was dark energy, the dark sky interval where there was no light. Hubble attempts to reach back there. And it has found redshifts of nearly 9 and speculation about a redshift of 11. To actually know if this redshift is correct, you have to have enough light in that source to do spectroscopy. If you just see a bright light, you don't know its recession velocity unless you can see the spectral lines of recognizable elements like oxygen or hydrogen or iron or whatever. But some work derived from Hubble measurements has reached back here. James Webb immediately went beyond that and found a redshift of close to 13. And again, in lecture 6, we will discuss this in more detail. And this is important because when you get to high redshifts, like between 8 and say 20, now you're looking at objects receding from us at around more than twice the speed of light. And that also tells us something about when these galaxies formed. Now, I've shown you this before, but again, let's talk about it in a little more detail. This is redshift. Remember, again, a redshift of 0 is now. A redshift of 3 is 11.5 billion years ago. And these data points come from 2 different strategies for measuring properties of quasars. The baryonic acoustic oscillation comes from matching warmer and cooler spots on the cosmic microwave background with clusters of galaxies. And you see, and they have a particular measure here related to the Hubble constant, h. And you see the average point they're getting with bigger error bars the farther back you look. That is not a surprise. It's harder to get details on something that's far, far away. So you get big error bars, but the center of each error bar is this round circle. So baryonic acoustic oscillations provided this data, this color code, black for the black points, gray for a different use of a particular telescope to do this in more modern galaxies with lower redshift. A couple of points from yet another set of observations of baryon acoustic oscillations. We get these 2 points. And we get one from looking at a quasi-stellar object right here with a large error bar. But you can see the trend here. And here's a measure, this green dot is a measure of the local expansion rate, looking at something that's, say, 500 million light years away. That's called local. So we have redshift to express this data, and we are now going to overlay the results from the Friedmann equation using the best values we have for the density of matter and the density of dark energy of 0.3 and 0.7. And that's this green curve. And the green curve is right on top of these data points, which gives us confidence that we're doing the right thing. If you chose other parameters and put them into the Friedman equation, you see big differences from the observed data. And we're fortunate the universe behaves in a way that if you turn the knob from these two values that we've measured by various different techniques, as I described in the concordance page, if you turn the knob and say add more matter and less dark energy so that you have this equal balance, you're nowhere near the observed data. If you use these values, you're closer, but still the only one that really works is this particular set of data. So we're fortunate that the Friedman equation is very sensitive to the selection of these numbers for matter and dark energy. And when we use the measured values, we're right on top of the data. So that's encouraging. We have these values for the expanding universe. In the age, 13.8, no curvature, comes from a cosmic microwave background. The Hubble constant derived from the cosmic microwave background is on the low end of what we're getting. We don't get this number when we look at supernovas, but the supernovas don't come from the entire universe. They only come from relatively nearby. So maybe that's an issue. Here's the fraction of the universe that's atomic energy, so-called baryonic energy. It's about 5%. Dark matter, we now know, is close to 26%, giving us a total for matter density in the universe of 31%. The rest is dark energy. Here's the redshift when the universe became transparent. This has been measured using the cosmic microwave background. You see, I usually abbreviate this as 1100, but there's the actual detailed number. And that happened this number of years after the Big Bang. So we really have this pie chart. And there's different versions of the pie chart depending on when the chart was drawn. But we have atomic matter, 4.5%, dark matter, 23%, and the rest is dark energy. In the early universe, the universe was very small compared. It was 1,100 times smaller than it is now in dimension, which means it was over 1 billion times smaller in volume. And dark energy was essentially non-existent because dark energy depends on the volume of the universe. And the volume was 1 billion times smaller in the early universe. So we don't even see dark energy on this graph. So in the very early universe, dark matter was prominent. Lots of photons, high energy photons flying around, breaking things up. There was atomic matter and neutrinos, which are these weird particles that are associated with the different versions of electrons that exist in the universe. So we've evolved from the very early universe, this pie chart, to this one. And remember, the pie charts are not the same size out in nature. The universe is 1 billion times more voluminous now, and atoms have been created in stars and so forth. So, but this is the pie chart that existed near the beginning. Now, one of the wacky things that we find that results from Einstein's equations is a violation of our intuition. It's obvious to all of us if you are talking to somebody and they're standing next to you, they have a particular size, and if they walk away from you, they appear to get smaller. I'll use this drawing of a railroad track to illustrate this. The width of between the rails near you, it appears to be much larger than in the far distant area there. This is normal, but in a expanding universe, that's not the case. Nearby objects look big, and then as they move away from you, they appear to get smaller. No surprise there. But as they go way far away, they appear to get bigger again. And this comes from the curvature, the potential curvature of space that we have not yet detected. We don't know the shape of the universe, but we know that we're dealing with a flat geometry. And there's a way to try to explain this, and that's with this sphere. Remember, we have to be careful about this, these analogies, but imagine your friend standing next to you has a meter stick and they show it to you. So, okay, how big is that meter stick compared to this latitude line that surrounds you both, and you're at the North Pole of this sphere? But it has a certain size relative to the size of the horizon. As they walk away there and hold up their meter stick so you can see it, the fraction of the horizon occupied by that meter stick gradually gets smaller because these latitude lines get bigger. But once they cross the equator, the latitude lines start getting smaller again. So if they could send you a signal when they're standing here showing the meter stick compared to the distance around this sphere, the length of the longitude, the meter stick would appear larger. It would in fact appear as big as it does here. And if they're at the South Pole, the light they send from the South Pole makes it look like the meter stick wraps completely around you. This is one of the crazy geometric features of our universe. Here's Einstein appearing over and over on the cover of Time magazine, dating back to the 1930s. Here he is depicted on the cover of Science magazine in 1998, when the discovery of perhaps of the century was made of an accelerating universe. It was the breakthrough of the year in 1998 and led to a Nobel Prize. But it's probably the most surprising thing we've ever discovered about the cosmos. And here are the three people that made that discovery. And all three of them are busy trying to figure out why we can't make a series of measurements of the Hubble constant agree with one another. That remains an unanswered question. If we had more time, I was going to go through this recent work from 3 years ago using James Webb, looking at Cepheid variables and nearby type 1a supernovae to extend the reach of this technique for building a cosmic ladder based on James Webb measurements, going far beyond what the Hubble Space Telescope was able to do. So we're near the end of the hour. Let me check and see if we have additional questions. Oh, and by the way, if you don't have the link to the class folder, let somebody in the OLLI program know, because that's where I post the Q&A. So in the next few days, I'll look through these questions and I will provide answers. There's also in every one of the lecture folders, because there's a folder for each lecture, there's a link to my YouTube channel where you can see the recording of what I've just presented this afternoon. And there's a class list, and and the lecture notes are in the folder. So everything appears in the folder. Again, if you're having problems with that, let somebody at OLLI know and they'll contact me. And that's it for today. It's 3 o'clock. I look forward to seeing you next week, and we'll explore another topic in a lot more detail. So that's it for now. Thanks.
Thank you, Ed.
Okay, good day.
Thank you.
Thanks, Ed. Great.
Okay, thank you.
Do you have your questions saved, Ed?
Let me make sure. I don't think anything technical came up. We're chat. Let's make sure that we have the technical questions. Let me get this out of the way. All right, I'm going to I'm just going to copy all this and drop it in this file, and then we can close this out. Okay.
Awesome.
Okay. Thank you.
See you next week.
Yes, indeed.